Hello, welcome to my classroom. Today we are going to discuss soil evaporation in the presence of water table and in the absence of water table, because these are the two realistic conditions existing under field situation. Now, before actually going for these two cases to be discussed separately, let me tell you that evaporation is an important component. We already discussed in our last lecture. This is an important component of the hydrological cycle. And of course, there is net loss of evaporation. That means we have precipitation falling to the earth, that is gain of moisture, and loss of moisture from the soil in the form of evaporation. But evaporation is always a net loss. It is a net loss. That means 50% higher than that of precipitation under arid conditions. 50% higher in arid conditions. And this 50% for the precipitation, what we receive. So that means if you have 100 units of or 100 millimeter of rainfall in an arid environment, the evaporation will be 150 millimeters. So ultimately it's a net loss. You are getting 100 millimeter, you are losing 150 millimeters. And when I say arid climatic conditions, that means very harsh climatic conditions. That means evaporativity is very high. Now we will discuss the first case, that is evaporation in the absence of a water table. I should not say a water table, because water table can never be absent. Better call it as in the absence of a shallow water table. So let me call it as shallow water table. Generally they say that in the absence of water table, in the presence of water table, but water table is always there, maybe at very deep depths. It may not influence the evaporation, but still we will take into account the shallow water table. Now in this case, while discussing that you do not have a shallow water table, then how the evaporation from the surface of soil will take place? For that we will have two assumptions. Assumption one is that your soil is initially saturated or wet. Better call it as wet, because the soil is never saturated under realistic conditions. So it is initially wet soil and very deep water table. As I said, water table is always there, and here the assumption is that water table is very deep. It's not going to influence the evaporation. And second assumption is that atmospheric evaporativity is constant, though it may not be constant. Because your evaporation rate, it may have certain diurnal variations, because the temperature, the wind velocity, it's changing over the diurnal period, over the 24-hour cycle. But even within a particular period of 2, 3, 4 hours, there may be drastic change in wind velocity, or there could be change in temperatures also, because whenever cloudy conditions are there, the temperature may go down like that, radiation energy may go down. So, but here we are assuming that atmospheric evaporativity, or as we discussed last time, that is the demand of the atmosphere for the moisture. So atmospheric evaporativity is constant. So keeping these two assumptions in mind, we will see that what happens to evaporation. Now again, you might be remembering this figure as we discussed last time. This is the relative evaporation rate, and here you have time. Now your soil is initially wet, okay, that means there is sufficient moisture, and let me draw a profile over here. So this is your wet soil. So let us say the root zone is very wet. Now there is evaporative demand. Evaporation is taking place. Now relative evaporation rate, it could be the first stage. That means with time, and this time period may vary depending upon the atmospheric conditions. Now here we say that evaporation, this evaporativity or demand of the atmosphere for moisture is constant in our study. So here what happens, that the relative evaporation rate, it will be constant, or in other words you can say whatever is the demand of the atmosphere, most of it is being met through the capillary rise of water. Now see over here, this is wet soil and evaporation takes place from here. So that means the soil gets dried up, the surface soil dries up. Once the surface soil dries up, still this stage continues. That means constant rate stage or stage 1 continues. This is your stage 1. And this stage 1 will continue. Now when you know this soil will dry, two things will happen. The potential, soil water potential between the surface layer and the subsurface layers, that's very high because it immediately becomes dry. So this is quite wet, the subsoil is quite wet. So there is a big difference in hydraulic potential, or you can say better called soil water potential. And if you try to calculate the hydraulic gradient between the two, so when your whole profile was initially wet, the soil gradient was very negligible. There was no driving force. But once the evaporation started, this gradient became very high. Now this is hydraulic gradient between the surface soil and the subsoil. So gradient becomes high. So moisture from the lower layers, it should rise up through the process of capillary. You know the Darcy's law. Darcy's law states that the flux of water. Now in this case, this is your flux of water. That means water moving up in response to the hydraulic gradient between the soil surface and the subsurface, which is very high. But at the same time, when this surface layer becomes dry, that means its moisture content decreases. What will happen to K? Because hydraulic, your flux is, as per Darcy's law, it is K theta. That means hydraulic conductivity as a function of moisture. And you know that hydraulic conductivity of saturated soil is maximum, and as the soil moisture content decreases, hydraulic conductivity decreases accordingly. So here is your potential gradient. So two things are there. Potential gradient is going to increase because of the difference in the moisture content. Surface layer becomes bit dry, then the subsoil, which is still wet, and due to, so hydraulic this gradient increases, but hydraulic conductivity decreases. Now what should happen, that because of decrease in hydraulic conductivity, the flux of water should decrease. But because there is increase in hydraulic gradient, so the decrease in hydraulic conductivity is being balanced by the increase in hydraulic gradient. So ultimately the flux will take place. So water moves up to the surface layer and it meets the evaporative demand. Till this process goes on, I mean decrease in hydraulic conductivity is compensated by increase in hydraulic gradient, this stage will continue. It will last. It may last for 2 hours, it may last for 1 day, it may last for several days. It depends upon the evaporative demand of the atmosphere. If evaporative demand is less, this stage may last longer. If the evaporative demand is high, this stage may last for a shorter period of time. So I hope, did you get my point? So stage 1 in the absence of a shallow water table will be lasting till the decrease in hydraulic conductivity is compensated by increase in hydraulic gradient, and upward flux of water takes place through the capillary process and water rises up to meet the atmospheric demand. Once, now again what happens then? Now as this subsoil also goes on drying. So what I should say that if this becomes dry, this becomes bit dry. So ultimately most part of this subsoil becomes dry. Now surface is also dry, subsoil also becomes bit dry. So with the result, the hydraulic gradient, it narrows down, it decreases. Earlier there was very sharp difference in the moisture content of the surface and subsurface layers. But with time, as the subsurface also gets dry, this hydraulic gradient decreases. Now this hydraulic gradient decreases, and of course hydraulic gradient conductivity should also decrease because moisture is decreasing. Now both are decreasing at the surface, so the water rises to a very small extent or may not rise. With the result, stage 1 will end up and there will be sharp fall in evaporation rate, relative evaporation rate till it enters stage 3. So here you have stage 1, here you have stage 2, and here stage 3. So now stage 2, as I said in my previous lecture, stage 1 now will be controlled by the evaporative demand. Stage 2 will be now controlled by the profile characteristics, water conducting properties of the soil. And water conducting properties of the soil, they depend upon hydraulic conductivity, as we discussed in our previous lectures. If you remember Darcy's law, so water movement in unsaturated soils. So the hydraulic conductivity is a function of permeability and fluidity. So permeability depends upon the properties of the soil, fluidity depends upon the properties of the water. So in both cases, so hydraulic conductivity becomes the determining factor. Now if hydraulic conductivity becomes a determining factor, then it means hydraulic conductivity, it's a function of soil texture, and again it's a function of soil structure also. So the hydraulic properties of the soil, they determine the evaporation rate in stage 2. And as the moisture content decreases, maybe in a clay loam soil, your stage 2 may last for a longer time. It may go like this. Say if this is loamy sand, say that it is sandy loam, and if you have a clay loam, then stage 3, this is now clay loam. Now why this stage 1 in clay loam, it lasts for the longest of the period of time? Because there is capillary fringe, there is dominance of micropores in clay loam, and it's under unsaturated conditions the hydraulic conductivity of finer textured soils is higher than that of coarse or medium textured soils. So water remains rising up to the surface. So that's why finer the texture of the soil, longer will be the period of stage 1. And then as the water content, the increase, the uprise of water in the profile to the surface, it decreases because of decreasing hydraulic gradient as well as hydraulic conductivity. Stage 2 starts. Similarly, I can say that if this is your, say, I should call evaporativity, say evaporativity 1, this curve is for evaporativity 2, this curve is for evaporativity 3. And now, can you tell me that in which case the evaporativity will be the highest? Yes, in stage 1. That means evaporativity of stage 1 is higher than evaporativity of stage 2 is higher than evaporativity of stage 3. So lowest the demand of the moisture in the atmosphere, demand for water in the atmosphere, higher will be the period of stage 1. I hope the things are clear now. And stage 3, as I told you, it doesn't matter because whether the soil texture or whatever it is, because in stage 3 water mainly moves in the vapor form, and vapor movement of water is negligible, so we generally don't consider this to be. So this is how the in the absence of water table, shallow water table, this goes on. In other words, I should say that what during this process, what happens to the profile moisture. Now supposing that this is soil depth and here it is theta increasing in this direction. Okay, soil depth like this. Now at time, this is say time t0, so I should say initially wet soil. Then evaporation starts, the moisture content of the surface decreases, say it's time t1. Then again after some time the moisture content further decreases, it is t2. Then again t3. So as the time goes on, the moisture content of the surface layers, it goes on decreasing, and then at T4 it could be like this. This is T4, and now here this is say now the water is not rising. There is a decrease in hydraulic gradient as well as hydraulic conductivity. So then the moisture at the surface remains almost same, T5, T6, and the lower layers they start decreasing. So that means if this is the moisture content decreasing in the profile, so then this is your drying front. So as we, if you remember in case of infiltration, we studied how the wetting front moves down. Now here how the drying front moves down. But under realistic conditions, you may have, after immediate rainfall, you may have infiltration also, you may have evaporation also. So this is how you can express the decrease in soil moisture content over the drying periods. So again, during the initial stages, T1 to T4, it depends upon the meteorological conditions, depends upon the evaporative demand of the atmosphere, and T4, T5, T6, T7 onwards, it depends on the profile characteristics, water transmission characteristics I should say, how it depends upon how the water is transmitted. And if I should say that in clay soils there is more evaporation, total evaporation, than in medium texture and least in coarse textured soils. So this was about the evaporation in the absence of a shallow water table. Then second case is evaporation in the presence of shallow water table. Now here, if you have a water table, I should say explain it in diagrammatically. So here evaporation again will take place in the form of 3 stages. But here the difference is that in this case it could be steady state. We also call this as steady state evaporation. That means evaporation taking place at a constant rate stage, because shallow water table is there. Now here the water has to take place in the profile. I should say, if this is your profile and this is, say, the water table at 90 centimeter depth. At a shallow depth you have a water table. Now the water below this water table, the soil is saturated. So this is saturated soil. And above the water table there is capillary fringe. This is called as capillary fringe. Now this capillary fringe it may be up to the soil surface, depending upon the texture, depending upon the water table. If shallow water table is a bit lower, then maybe this capillary fringe may not reach at the surface. If it is at 90 centimeter, then it may be even up to the surface. So in nutshell, what I mean to say is during the presence of a shallow water table, the water has to move through a saturated layer or saturated zone, then capillary fringe, and then unsaturated zone. Now this steady state evaporation rate, that means when evaporation rate neither increases with time nor decreases with time, that's why we call it as steady state. That will depend upon two things. So I should say steady state evaporation. It depends upon two things. One, it depends upon the depth of water table. Deeper the water table, lesser will be the rate of evaporation. Although it will be a steady state because shallow water table is there, but then shallow water table again may be at different depths. Like we have 90 centimeter, it could be at say 120 centimeter, it could be say at, this is your water table, this is water table maybe at 180 centimeters. So even up to 3-4 meters we call it as shallow water table. So 180, this shallow water table is also varying at different depths. Now as I said, it will depend upon depth of water table, number one. Second is the suction at soil surface. So when I say suction at soil surface, ultimately it means the demand for moisture or water potential. Now at the soil surface, here it will be evaporativity. If your evaporativity is harsh, atmospheric demand for water is high, then steady state evaporation will be at a higher rate. So as this suction at the soil surface means, again you can say it is demand of water at the surface of the soil. So then evaporation rate will be high. So here it is, I will be on the x-axis, I am showing soil suction in centimeters. Say it is 400, then 800, then 1200, 1600 and 2000 centimeters. Means after 2 atmospheres. And again it will depend upon, as I said, the depth of water table. Now here, supposing this is your depth of water table 90 centimeters. So water table 90 centimeter. And this will be very, very sharp, because water table is shallow, evaporative demand is there, and this is the evaporative demand over here. If we increase the evaporative demand, there will be very slow increase in evaporation rate. You are increasing suction from say 400 to 800, the evaporation rate may be not more than, so I will change the evaporation rate, this is say in millimeters per day. So the evaporation rate may be increased like this, then it will become steady. So if it is over here 8, then 6, then 4, then 2, then 0 over here. So you can see that at a particular suction level, they say it is 6. If you increase the suction rate from a very low value to 400 centimeters, there is very small increase in the evaporation rate when your water table is at 90 centimeter. Now if your water table is at say 120 centimeters, say over here, so this is your water table at 120 centimeters. So that means now water table has gone down. So in this case also there will be very small increase in the suction rate, and then it will become steady. Still, that means water is rising up as per the demand, but even if the demand increases, the evaporation rate is not going to change. After this value, say 500 or 600 centimeters of suction, or in other words, centimeters of evaporative demand, then there is no further increase in evaporation rate. This is a very important point. Here also, though the steady evaporation rate is 8 millimeters, but it increased from 6 to 8 by increasing the suction from 400 to 800. So, how harsh the climate is, the evaporation rate is not going to increase. But the reason, it is limited by the profile characteristics again. Because it is the profile characteristic which limits the rate of evaporation. And though the demand is very high, but still the evaporation rate will be steady at a particular value. Now if you are further lowering this water table, so here water table is 180 centimeters, and again the evaporation rate, it behaves in the similar way. Though the evaporation rate is less than 2 millimeter per day, it is steady, but even if you increase the suction at the surface of the soil, there is no further increase in, because it depends on the profile. So that means it's not matching, the demand is not matching with the supply, because supply is limited by the profile characteristics. So whatever may be the demand, how harsh the evaporativity may be, still there is a certain maximal value of evaporation rate. This is how your evaporation, it depends upon the profile characteristics. So water table, if now water table is shallow and suction at the surface decreases, then evaporation rate will be equal to demand. So here in this case, suction decreases, is shallow. Here you can say this could be equal to the demand of the atmosphere. But as the water table becomes deeper and suction increases, then evaporation rate approaches a limiting maximal value, that is less than 4 over here, less than 2 over here. So this is all about the evaporation from the soil surface with a shallow water table, without a shallow water table. I hope the things are clear. Thank you very much.